All right, here's our topic, and here's our objective. Remember from the e-guru that when you were stressed out an equilibrium system in equilibrium, it tends to do the opposite. And this is just examples of it. Now, when the stress gets it out of equilibrium, there's two ways the systems are going to respond. And the way the stresses themselves, one will affect I shouldn't have said two ways it will respond. It's two ways the stress, they either affect the K or don't. Those that affect the K are temperature related, and those that don't are concentration related. All right, so here's our first stress. We're going to add a chemical. Now, here in a moment, you're going to see chemicals being added. There's iron and thiocyanate. This red is the thiocyanate. All right. Now, uh, there it is. Now, in a moment, I'm going to add more of one of these chemicals. In this case, I'm going to add more thiocyanate and watch what happens. There it is. Boom. All right. How did the system respond? It got rid of the thiocyanate. It got rid of it by turning it into thiocyanate, which is this complicated ion. That's what gives it that red color. All right. Now, this is just from like a particular drawing. I get these ions in, equilibrium is established, and now I've got this red. Now, I add more thiocyanate. You might be asking yourself, what's the system going to do? Well, the opposite of adding is subtracting. And the only way that the system knows to get rid of these thiocyanate is to turn them into these these thiocyanates, to turn them into the iron thiocyanate ion. All right. And boom, it does it, and it gets darker. All right. Now, for this next stress, we are going to remove a chemical, opposite of adding. And thank you, Ryan. But you'll see that cloud there moving down through it? There it is. Boom, that little cloud, that's a precipitate reaction. And um, when you precipitate, you remove the chemical because now it's no longer, it's a solid, and solids don't uh, act in the equilibrium equation. Now here I've added a bunch more. I added it a little more aggressively. All right. And the answer to removing is replacing the chemical. All right. Now, here we go. We got this red color. We got iron thiocyanate. Now, I was adding hydroxide. Hydroxide and iron form an insoluble compound. All right. And then what do things that are insoluble? They fall out of the water. All right. And they precipitate out. Beautiful reaction. And this is going to be like, hey, I lost some chemical. I need to replace it. All right. And the only way to replace these irons that have been lost is to break apart these complexes between iron and thiocyanate. So that's what's going to happen. I'm going to break it off. It's going to turn pink and be clearer. Now you can see here is the solution before I added the hydroxide to it. It's a brighter. And here it is after. If you look, they're kind of, the one on the right is lighter because I've taken out some of the concentration of the iron thiocyanate because it had to turn into iron. All right. This was a precipitation. Now you can also neutralize a reaction. You can do a neutralization reaction. This is one. All right. So you've got two chromate ions. This one that uh, is orange. This is yellow, and so it's this one. And what you can do is if you add hydroxide to this equation, to this solution, you know that hydroxide is and hydronium or protons are going to make water. And when you add that, you're removing it by neutralizing it, and then the system is going to want to make it to So there, it makes it and it turns it yellow. All right. So here's what the solution looks like. All right. It has all these ions. These are the ones that make it orange. All right. And then what do? I add some hydroxide. What does the system do? It makes water. All right. And then if it lost some of its H here, it needs to replace it. So it has to make it with this, and it makes that, and then this is eventually, and I'm going to end up with more. Now this is what makes it that orange color or that yellow color. All right. Sorry. Um, and so I am removing it by a neutralization reaction. Now the next type of stress, and these are all stresses of concentration, is when I dilute or add a solvent. Here's what it looked like before, and here's what it like when I added a lot of water. What did the system do if I dilute it? It's kind of interesting. What it tends to do is it tends to make more dissolved species. Now, you're right to think that this is not, if I dilute anything, it's going to get um, dimmer. However, sometimes you could actually be making a darker color depending upon the reaction. All right. So here is, you've got iron thiocyanate. All right. Here's what they look like at equilibrium. All right. And when I add water, the molecules are going to spread out. What the system wants to do is kind of establish the same kind of concentrations that it had in lieu of the equilibrium constant. All right. Now here, if you look at this, here's our equilibrium constant. You'll notice there are two dissolved species. So this will have a greater effect in the denominator than in the numerator by changing the volume. This is going to go down by a factor of 2 or twice as much as that. Therefore, that the only that's going to make the equilibrium constant, or the Q, the reaction quotient, not the equilibrium constant. Therefore, the system is going to want to make more of these species. All right. It's going to want to spread everything out. All right. And make more of the of the uh, of the uh, dissolved species, or like dissolved aqueous species. Now, when I remove it, it's the opposite. You're going to want to go to make less dissolved species. So I want less things dissolved, like less more molar wise. All right. Now, for gases, this is another way to influence concentration. I can increase the pressure by decreasing the volume. Now, what is this? Here's a system. All right. How would I decrease the volume? I'd shrink it down, right? And let's just say this is our uh, our equation. If you put all these things in this box, you're going to know the pressure is going to increase. The system gets this sense of pressure increasing, and then what it wants to do is it wants to decrease pressure. The only way to decrease pressure through equilibrium is to by make less moles of gas. So which side here favors less moles? The right side, because for every 2 moles, I have 1 mole. So what's going to happen is it's going to make more of the product in this case. All right. Now the opposite, if I decrease the pressure or I decrease the volume, excuse me, I decrease the pressure by increasing the volume, the system's going to increase the pressure, so it's going to want to make more moles of gas. All right. Now, all of those were influences of concentration, and none of them affect the K. Now we're going to move into those that do. Um, those being your temperature ones. All right, I've got a cobalt chloride. All right, cobalt chloride. As you can see, it's kind of blue. It's shifted towards the right side of the equation. When I heat it or when I cool it off, you can see it changing. You can see the blue and the pink, and eventually it turns all this pink. It makes this cobalt with a 6 waters complex. And then when I heat it up, all right, on a hot plate, what's going to happen? It should go back to this. All right, it turns back to my blue. Now, this isn't, we're manipulating an equilibrium by getting a new constant, by affecting the constant decay. All right, so here I have this blue, I have this solution at equilibrium. What's the stress? I add heat to it. All right, what does it do? It turns blue. And what it's doing actually is it's favoring the endothermic reaction. All right, and here's a little, uh, let's just pretend this is our equation. All right, I've got these chemicals. You can see it's shifted. I've got more one than two. And if I start to add heat to it, it wants to get rid of the heat. And the only way that the system can get rid of the heat is by turning chemical one into chemical two. All right, and that's what's going to happen. All right, now the opposite is the same. Or is is the opposite. If I remove the heat, it's going to want to go to the endothermic. I took this blue thing, I cooled it off, and now I've got this pink thing. So here I've got my chemical or my equilibrium. Now I put surround it, I make it cold. The chemicals, in this case, chemical two is really some latent energy that's stored in the bonds of the molecule, and it, this cold, what it's going to do is it's going to draw this heat out from some of the molecules such that it shifts the equilibrium towards the exothermic process. All right, and that's what it does. So here are my sources, and thank you very much.